Alright, let's have a look at solving systems of linear equations, and this is probably all going to be review for you. A system of equations can also be called simultaneous equations, is a group or collection of equations in the same variables, meaning that all of the equations would have possibly an x and a y, or maybe all of the equations would have an a, b, and a c. You might have zero of one of those variables, so it doesn't appear in a variable, but we are dealing with the same variables in that collection of equations. The solution of a system of equations in, let's say, x and y is any ordered pair, and you'll see those make the coordinates on a graph, x, y, satisfying all of the equations in the system. So it must satisfy all of them simultaneously, hence they're known as simultaneous equations. Since each linear equation could be graphed, the solution, x, y, is also the point of intersection for the graphs of the lines in the system. And so let's have a look at this for a moment. So if I've got one line that looks like, say, this, and I've got another line that looks like this, then the place where they intersect is going to be the coordinate xy, which will satisfy your first equation. And so if I substitute the x here and the y here, I will get, yes, it works. And likewise, if I've got, say, dx plus ey equals f, and if I substituted the x and the y into this equation, then again it would work. This means that the point is on this line, and the point is on this line. Hence, the point must be on both lines and must represent an intersection between the graphs of the lines in the system. Now we can test whether a particular point is a solution to a system by seeing whether this point does actually satisfy both equations. Let's look at an example to this. Is 2 comma negative 1, is it a solution to this system? Let's see. So first I'm going to substitute the 2, negative 1 in for the x and the y. So I've got 2 minus negative 1 is this equal to my right-hand side of 3? This is a pretty informal way of checking. I'll have a look at formal ways of checking at other times, I think. 2 plus 1 it becomes. Is 3 equal to 3? Of course it is. This means that 2, negative 1 is on this equation. So that is a point on that line, if you think of it graphically. And let's test the other one. If we substitute in 2 for x, let's do it over here. 3 times 2 and negative 1 for y. Is this equal to 5? Let's see. So 6 minus 1, is this equal to 5? So is 5 equal to 5? Yes, of course it is. And that means that the point 2, negative 1 is also on this line. Hence, 2, negative 1 is a solution to the system. Now, if it satisfied one of the equations but not the other one, you might think of that graphically like this, that the point does satisfy one of the equations and thus appears on that line, but it doesn't satisfy the other equation. So even though it may be a solution on this equation by itself, it is not a solution to the entire system of equations because it's not a solution to every single equation simultaneously. Now, if a system of equations has no solutions, then it is known as an inconsistent system. And graphically, the lines formed by the equations would be, so if you try to imagine two lines that have no solutions, they never overlap, ever, no matter how far you go, what must they look like? They must be parallel. And there's a picture of that down here. Here's parallel lines. So you see they never intersect. That means that there is no solution. And we call this an inconsistent system. On the other hand, if the system has at least one solution, it is called a consistent system. So, inconsistent, no solutions. Consistent, there is at least one solution. Now there's two ways we can have a consistent system. If the system has exactly one solution, then it is called a consistent because it has a solution, it is consistent, independent system. And graphically, the lines formed by the equations would look like this. This is consistent, independent. It's consistent because there is a solution, and it's independent because there is exactly one solution. And so the lines formed by the equations, we can see, are going to be intersecting. However, if the system has infinitely many solutions, then it is called because we have at least one solution, it must be consistent. And you can probably guess what's another word opposite of independent. It's of course dependent system. And graphically, the lines formed by the equations, if you imagine two lines where every single point on each of the lines is a solution, that is to say, a place where the two lines are intersecting, obviously the lines are overlapping, aren't they? And we call this coinciding lines. Now this is a pretty easy solution to describe. We can just set up a set of coordinates. Maybe the solution is 3, -1 or something. Fine. That's the solution. Finished. It's a little bit more difficult to describe the set of solutions here. If we just said infinitely many solutions, well, you haven't actually told me what those infinitely many solutions are. You wouldn't say over here, there is one solution. Well, I mean, isn't it more interesting to say what that one solution is? So just like over here, it's going to be implicit that there's infinitely many solutions, as if you describe your solutions in such a way where you're talking about all of them. And how can I describe this set of points here? Well, this set of points is describable by an equation, and so perhaps this is the equation 2x plus 3y is equal to, say, 6 or something. Then this would be the set of solutions. So we might say, if we were going to do it in proper formal set notation, we might say, okay, our solutions are all coordinates x, y, such that 2x plus 3y equals 6. That is to say that this rule is abided by. So we're looking for any coordinates x, y which follow this particular restriction. And that's how we could describe the solution set of places where these lines are overlapping. Okay? All right, let's do part B. Let's classify these systems of equations. One way of doing this is to have a look at the slope of each of the equations, or even better, why don't we just change them both into slope-intercept form? And so this one here, if I isolate the y, it's going to, if I divide through by -2, I get 1/2 x minus 3 over 2. And my other equation, if I, my y is already isolated, that's convenient, so I've still got 1/2 x plus 4. Now if you have a look at this system, remember this equation has now become that, hasn't it? So this is now my new system. What do you notice about the slopes? They're the same. The slopes are the same. This either means then that the lines are, because they're going in the same direction, they're either going to be parallel or they're going to be the same line. In this situation, which is it? They must be parallel lines because the y-intercepts are different. If the two equations had been exactly the same, well, that would be a case where we have infinitely many solutions, and we can use either of these equations to describe that solution. Okay? I just noticed that, I don't know why I lost a little piece of this. Oh, there it is, it appeared again. Okay. Let's have a look at the second example. If I isolate, well, the y is already isolated in the first equation, so I just have to work in the second equation. And so if I move the 2 to the right, it becomes a -2. Let's distribute the -3 to the x and the -3 to the -1. Oops, sorry, becoming a +3. Bring over the 2, it's a -2. And that gives me y equals -3x plus 3 minus 2, that's +1. So what do you notice about our first equation and the simplification in slope-intercept form of this equation? Well, of course they're the same. And because these are the same, then we have infinitely many solutions. I could classify this then as a consistent dependent system. And the solution happens to be this circle thing right here, this set. So all coordinates x, y, such that y is always equal to -3 times the x coordinate plus 1. So that's one way you could describe the solution set. I forgot to classify the first system. I said it, but here it is. They're inconsistent. That's the classification of this system because, of course, we got two parallel lines. All right, so let's graph and then classify these systems. And so we're going to do this, I suppose, with a graphing technique. I'd like to do this on the calculator. And so I just will first need to rearrange the second equation. I get y equals -2x plus 4. And so in order to graph it then, I'll put in these equations. Y equals -2x plus 4. And, well, I forgot the first one, didn't I? Y equals 3x plus 4 was the first equation. So I've written these backwards, but it doesn't matter. 3x plus 4. There we go. If we have a look at this picture, there is the first graph, and there's the second graph. So it's pretty apparent from that picture that they are intersecting lines. You could have concluded this, of course, from here. Different slopes. Anyway, they're intersecting lines, and therefore, if we can classify this as a consistent, independent system. And it says then, find the solutions from the graphs. Okay, so I need to find out where these two lines cross. And I can do this with second trace. In the calculate menu, I'll choose option 5, intersect. I just go enter, enter, and look, I think they intersect where x equals 0. Let's see if I was close. And, oh, look, I was spot on. They do intersect at the coordinate 0, 4, which really shouldn't be a surprise to us, because when you look at these two equations, the y-intercept was positive 4 both times. So if they've got the same y-intercept, that must be the intersection point, because slopes are different, they intersect. In the second situation, my second equation has already got its y isolated. I'm a little bit nervous about the decimals, but I'll handle that in a minute. In the first equation, let's get the y alone by bringing the x term to the right. And that will become then, as I divide by -5, it will become 2/5 x minus 6/5. So you'll notice that because I've got fractions in my form for the first equation, maybe it'd be nice for me to change my second equation of 0.4x minus 1.2. Perhaps I should change that also into fractions. So 0.4 I know is 2/5 x, and -1.2 I can find out is 6/5. So, well, look, I've got the exact same equations. Because the equations are identical, it must be a consistent dependent system. So there, I've classified it, and then I need to find the solutions from the graphs. I've actually realized I haven't solved the problem like I was supposed to, have I? In order to give evidence that I graphed it, I should really draw a sketch of the graph. And so here we go. There's my line y equals 3x plus 4, and here's my line y equals -2x plus 4. And here, that's the point where they intersect at 0,4. There we go, that's solving by graphing. And on the second one, if I graphed it, I'm running out of time on this video, I only get 15 minutes, so if I graphed 2/5 x minus 6/5, I'd end up getting the same thing twice. They're coinciding lines, hence it's a consistent dependent system, and I can describe the solutions as all x, y, such that let's see, I can use the original equation, 2x minus 5y equals 6.